Hey guys, in this video I'll be showing off a cool pre-calculation technique that you can use that runs in linear time, so it's O of n, and it's pretty useful in um, making what might seem like an O of n squared um, problem and turn it into an O of n solution. So first of all, what does this technique let us do? Well, in an array, it is often useful to know the index of the first element to the left or the right of it that is smaller than the current element. And it also works for larger, but for this example, I'll just be going over mapping the index of the first smaller element. So, for example, if our array was 1, 4, 5, 2, 2, 3, we would make two arrays here, one with left and one with right, and left, the numbers in there, stores the index of the first number that is smaller than the element at that index and to the left. So for example, in the first index of left, so left 0, that would store -1 because that represents there's no number to the left of it that is smaller than it, because obviously there's no numbers to the left of it. And for index of 1, so the element at the array index of 1, um, if that's a 4, then the left array here would store a 0, because the index of the first number that's smaller than 4 to the left of it would be array index 0, because that's value 1 that's less than 4. Same thing with 5. We know that 5, the index of the first number less than it is 1, because at index 1 there's a number 4 which is smaller than it, then 2 that maps to 0 because that's the 1, etc., and a similar thing for the right. So, for example, here for the first three numbers, 3, 2, and 2, starting from the right, of course, we know we just say -1 because there's no number smaller than it to the right. And when we see this 5, we know, hey, there's a 2 at index 3, and that happens to be the closest, the index of the closest, the closest index of a number that's to the right of our current number and still smaller than it. So basically, with these arrays, we can look at an index and be like, hey, at index 1, I know the first number that's smaller than index 1, and to the left of it is like index 0, and index 3 is the first number to the right of it. And this lets you know instantly the first number that's smaller than it to the left and to the right. And so how would we implement this? So first of all, of course, we would need our array, so let's just call it left in this case, and we would use a stack to store the index of the number just smaller than our current index. So to start off with, our stack would be empty, and so essentially we will loop through all the numbers in our numbers array, and basically here you don't need to worry about this while loop for now. We can just first look at our if and else statements, because those are, of course, what's going to execute first. So, well, first of all, the first number that we do, the stack will always be empty. So, left of index 0, that'll be -1. And then, of course, we'll skip that else and we'll push the index into our stack. So our stack will now hold index 0. And so basically our stack will hold a list of candidate indexes. So I know, hey, this index is a candidate for a number that could be smaller than the number at this current index. So now, of course, when we move into index 1, we'll know, hey, index 0 is a candidate. And so then we might find ourselves going to the while loop. And so what the while loop does is while the stack has numbers that are greater than our number at current index, we can just throw those away because um, we know those are greater. And since when we look at a number later on, uh, like, okay, I think it's gonna be easier if I just illustrate this with an example. So, uh, yeah, so, yeah, wait, let me just get this thing working. Right, so if we have our array here and we know we're storing a bunch of indexes, we know like this index here, if it's greater than this number, we can throw it away. If this one's greater, we can throw it away. This one's less, we don't throw it away, we keep that one. And then we add this guy to our stack. So now our stack will not have these, but it'll still have this, and it'll have this. And the reason why we could throw these away is because let's just say we have another element here. Well, case one is that this element here is smaller than it. And since we've pushed that into the stack here, we know, hey, okay, the index of the element just smaller than it is this one. But if this number is greater than it, well, we know that this number was greater than this number, and this number was greater than this number, so it's fine to just throw those away because there's no way that this number would be greater than this number but smaller than this number if this number is already greater than this number. So then we'll move on to the next candidate, which would be this number, because this number was less than this number, it might be less than this number, but it's not guaranteed. So if that's the case, if this number is less than this number, we would also put that over here, and then we would also throw this away and then put this. And if it isn't, we just keep on throwing this away because at the end of the day, we'll always push this guy into here, so we'll be able to basically use that information. So the next guy we look at, we can be like, hey, is this guy less? Um, if it isn't, well, I know this guy's greater and this guy's greater than this. So all these ones that we throw away, we'll basically essentially be able to skip and look at the next possible index that might be smaller. So that's why this pre-computation works so well and why it's so fast. And yeah, so going back to our presentation here, so that's essentially what our stack here is representing. Um, while this number at the front of the stack, so this index at the front of the stack, is greater than our current index here, we'll just throw those indexes away. And if we've thrown away all the indexes, then we know, hey, there's no numbers to the left of it that are smaller. Otherwise, we know, hey, okay, so now we know to store at this index, we peek at the stack to figure out the index of the number that's just smaller. And of course, at the end, we want to push in our current index because that just lets us directly compare the next element to what we just pushed in and use that information. And so basically, a similar thing would happen to pre-compute your right array. And here, you can make a new array, clear your stack, start from the other side, and it's just the same exact logic where if the stack is empty, you put a -1 there. Otherwise, the right array will store the index of the number just smaller than it. And of course, you could easily reverse this logic by just changing the greater than equals to like a less than equals, something like that, if you want to keep track of the first greater index. And of course, push in your current index and basically, yeah, it's just the same logic, but starting from the right. And here are some problems where this technique is used. I'll link them in the description below. I'll also most likely, yeah, I'll probably make videos on these problems because I thought they were pretty interesting. So when I get around to making those, I'll also link my videos in the description for you guys to like see how this technique is actually used in the problem. There's probably more problems, but I couldn't be bothered to like find all of them. But if I run across more of them, I'll link them in the description as well. So yeah, so go ahead, use this technique in some problems, and yeah, I hope you guys found it interesting and learned a little bit from this video. All right, thanks for watching.